We're going to start off this next chapter by talking about center of mass. Okay, and center of mass is kind of something we've sort of just assumed so far without really talking about. And basically, center of mass is the average location of all the mass that an object has. So to think about this, it might help to think of maybe if we have some object that's a one-dimensional object with made up of lots of little dots or atoms, say, and they all have the same mass and they're all equally spaced, which mine definitely aren't. The center of mass would basically be the average location of all of these in the middle of it. Okay? And if we were to find the center of mass, there's kind of two important things that we can know about it. The first is that we would be able to balance that object at that point. So if we were to place something under it to support it, the object would actually balance there at the center of mass. And if we were to rotate, that'd be the position where it's easiest to rotate. And we'll get more into that in future chapters, but those are two kind of features about the center of mass. The last thing I want to mention before we get into finding center of mass is this is also something we've assumed or been using the whole semester when we talk about kinematics, for example. Because when we do kinematics, say for a car, let's draw a real car. If we were to do kinematics about a car has a large volume, it's a complicated shape, and it's difficult to do physics when we have to talk about all the parts of the car. And so instead of doing that, we treat it as a point located at the car center of mass. And we do all the physics about this point rather than having to think about what the wheels are doing, how this piece right here is moving, how this piece is moving here, and that piece is moving there. If we wanted to calculate the location of a center of mass, and we're going to start by looking at a system of particles. So let's say we have a system of particles and we want to calculate the average location of their center of mass. What we do is we take each piece of mass and we multiply it by its horizontal position or its vertical position, and we add them all up together like that, and afterwards we divide by the total mass. So the formula looks something like this. We use COM for center of mass, and here's the formula written out. So we take each chunk of mass, multiply by its position, and continue to add it to all the other chunks of mass multiplied by their position, on and on for all the pieces in the system, and then we divide by the total mass of the system. And so what this does is it kind of tells us the average location of the mass. And so let's say this object here, M2, was more massive than everything else. It would have more weight in the equation or more effect on the equation because this value here would be bigger than the rest, and so it would adjust the average based on its location. Just like, say, this one was located farther away from everything else, it's going to pull the center of mass that way because this part will be bigger. Okay? So we're going to give this a try now. We have this scenario here where we have three objects of different mass, okay, and they're all located at a different coordinate. So we want to find the center of mass for the system, and it's going to be a coordinate somewhere in between all three of these. Okay, it'd be the average location of the mass. And so the way we do that, a coordinate, we're going to have a x component and a y component, and we'd have to find these separately. Okay, the order you do it doesn't matter, but you're going to basically isolate the horizontal values for center of mass and the vertical values. Okay, so we're going to go ahead and do this now. And I'm going to start by finding the horizontal center of mass, so the center of mass for x, okay, and then later you're going to do the center of mass for y. So remember that we're going to take each mass and multiply by its horizontal, in this case since we're using x, its horizontal position. So the first one would be 1.2 times 0. Okay, we're going to do it again for 2.5 and 140 It doesn't say on here. I'm guessing these are meters maybe. So 140 meters and 1.2 and 70 meters. Okay, so here I have the 2.5 kilograms times 140 meters. Let me put the units back in just a second. And then the 1.2 kilograms times 70 meters. Underneath now we put the total mass, so we'll add up all the pieces of mass. Okay, so underneath here now I have the total mass, or all the masses, 1.2 for the first one, plus 2.5 for the second, plus 1.2 for the third, and now we'll go ahead and simplify it. Okay, so I've gone ahead and I've done the calculations here. I multiplied each chunk on the top. I've added them together to get 434. The total mass of all the particles is 4.9 kilograms. I divide those and I find that the x center of mass, so that horizontal center of mass, is at 89 meters. So that means that if we look this way, if all three of these masses were just sitting on a surface like this, and you had this one right here, they would balance at a point about right here at 89 meters. Okay, so from here we need to find the the y center of mass. So I'm going to ask you to go ahead and do that now, and you're going to have a chance to submit your answer, and then once you do, I'll go ahead and just quickly show the work for it. At this point you should have found the location of the y center of mass. I'm going to go ahead and show it real quick, so in case you have any questions you can make some changes to your method. Okay, so basically you find the center of mass by adding the mass times position, in this case vertical position for y, for each of the pieces of mass in our system. These two were at 0, this one was at 120 meters up. Maybe they're centimeters, that might make a little more sense here, but anyway, underneath we have a total mass. Our total mass, we add them all up, we get 144 over 4.9 for a position of about 29 meters. So now we have the coordinates of our center of mass. Okay, that puts our center of mass, so it looks like the horizontal position is about the same, 60, 70, maybe 82, but the vertical position would be down about right here. And so the reason it's different is because I actually changed the value of one of the masses from the example. So this would be that position for the center of mass, though, or the average location of the mass of these three particles.